So where we were in the notes is we were up to looking at properties of the derivative. And there were four key ones, which are all about how the derivative behaves with the operations that we have that we can perform on functions. So we can take basic functions and construct complex compound functions using the operations of addition of functions, multiplication of functions, quotients of functions, although really that's multiplication in a sense, quotients, and then a key one, the chain rule. The chain rule is about how the derivative behaves on compositions of functions. Okay? Complex functions built up as the composition, running one function after another one. Okay? And we've already looked at some examples of working with this last week. Examples there on page 43. That might have even been the previous week. And we also looked at, even before we proved the chain rule, we used it to prove the quotient rule. So last week we just assumed that we had the chain rule available, and we worked on constructing a proof of the quotient rule using that. And we also looked briefly, and you did in the tutorials as well, on some kind of applications of the chain rule and some of the other rules, such as getting derivatives of inverse functions, parametric or slopes of tangents to curves defined by parametric equations, logarithmic differentiation and implicit differentiation. Okay? But now all of these are, lots of these rest in one way or another on the chain rule. So we want to see a proof of that. We want to be assured that it is indeed true and that we understand and we can appreciate how the truth of the chain rule follows from the definition of the derivative and what the derivative is. And we did try this last time. So at the end of the last lecture, we did here, you can see there on the board, a first attempt to prove the chain rule. I mean, I knew it was going to fail, but, why couldn't we go ahead and prove the chain rule just like we proved the product rule, the linearity result, just like we've obtained the derivatives of some basic functions? Why couldn't we do that? So this is the chain rule here in this red box, written in this notation. So if f is a composition of functions g after h, derivative of f of a should be the derivative of g evaluated at h of a multiplied by the derivative of h evaluated at a. That's the chain rule. There it is. It's a simple equation involving derivatives. Why can't we just jump into the definition of the derivative and hack it out straight away? Well, we tried to do that. So there's the definition of the derivative of f. This is all in last week's notes, the limit of the relative change in value of f. So we should, the only thing to do at that stage would be to substitute in the definition of f. F is defined as the composition g after h. So f of x is g after h of x. F of a is g after h of a. We have to take the limit of this, but here we kind of ground to a halt in that we couldn't really see any way to unpack the g and the h and to get the g and the h away from each other in a way. When we were dealing with linearity or products, what we meant at this stage was like linear combinations of functions or products of functions. And there, just using some algebraic properties, we were able to work with that expression and get it into the required form to obtain the necessary result. Whereas here, because we don't have any information about what the functions g and h are, we're just assuming that they're functions that have derivatives. And constructed like that, there's no obvious next step to take. And this kind of grinding to a halt there makes it clear that we need something else. We need a little bit of a different way of looking at this. And that's where we're going to go. That's what I'm going to go through with you now to discuss. And what it depends on is coming back and looking again at the definition of the derivative and trying to get a little bit more out of it. Trying just to expose a little bit more of the detail that is in the definition of the derivative. Okay. this is towards the proof of the chain rule. So our first step is, as I said, to return to the definition of the derivative. So we'll consider again the definition of f prime of n. Just thinking f is just a general function. What was the definition of the derivative? Well, it was differentiable if the following limit exists. So this was the definition of the function being differentiable at a. If the following limit exists, then we say it's differentiable at a, and if the value of the limit is the value of the derivative. Okay, that was it there. Okay, so the first thing we're going to do is just rephrase this slightly. So this is equivalent to saying that the derivative of f at a is the limit. And now we won't see here we were dealing with x being a separate point close to a, and we were taking the limit as that other point x converged towards a. Now we're just going to express it slightly differently. We're going to take the limit as k goes to 0 of f of a plus k minus f of a over k. Now this might, if you've not seen this before, this might look a little bit mysterious, what we're doing. But all we're doing, I mean, here the kind of picture for this definition, you've got the fixed base point a, and you've got another point x, and the x is converging to a, and you're looking at the difference f of x minus f of a, and you've got the difference x minus a. So x minus a is the signed distance between x and a on the bottom. Whereas here in this picture, it's exactly the same process, but just set up with the notations differently. Instead of using x for the other point, we use a plus a little a plus k to refer to the other point. The k could be positive or negative. That would affect which side of a the other point a plus k was, of course. And we're going to let that point a plus k converge to a, and that is done by taking the limit as k goes to 0. And instead of x minus a, see, x minus a is the signed distance here. Well, of course, the signed distance here is then simply just k. So it's exactly the same limiting process. That's the first thing to do. Exactly the same thing, just expressed differently. And just in a more amenable way to move towards proof of the chain. Okay, but that small change isn't enough. We have to get something more about this. So the definition of the derivative is that this limit exists. Alternatively, we can phrase the definition of the derivative as saying that, so this is a slightly different way, there exists a number f prime of a. So we have our function, we can look at its value at a, and this time we're going to phrase the definition of the derivative as saying the function is differentiable if there exists this number f prime of a such that the difference function epsilon of k. Now, what is epsilon of k? Epsilon of k, so this is a function called epsilon. Depends on the parameter k, and it is simply the difference between these two quantities. This difference function, defined like this, satisfies epsilon of k goes to 0 as k goes to 0. Again, this is another bit of a mouthful. What I'm putting in the box there, what I'm putting in that red box, I'm claiming that that's equivalent to saying to the original definition of the derivative. It's a bit of a more long-winded of saying. So originally we said the function is differentiable if that limit existed. This time we're just unpacking it a bit, we're exposing a little bit more of it. And we're saying, well, if we look at the difference between these two quantities, the relative difference evaluated at a nearby point, a plus k, we're saying that there exists some other quantity, some constant f prime of a, such that this difference function between these two things converges to 0 as k goes to 0. So saying that the difference between these two converges to 0 as k goes to 0, that's the same as saying that in the limit as k goes to 0, this number is equal to this. Agreed? Here we're taking the limit of this quantity and calling it f prime of a. Whereas here we're taking the difference between these two quantities and saying, well, as you take the limit as k gets small, because this one is converging to this one, the difference will converge to 0. And so we rewrite again, and we rewrite once more into, the way we're going to rewrite it now will be quite interesting and quite informative. As saying, so now we're going to say, we're just going to cross-multiply some parts, move some stuff around. We're saying, so we're going to multiply both sides by k, and then move everything else over to the other side. We're going to say f of a plus k is going to be equal to f of a plus k times f prime of a plus k times sine. Okay, so what I've done there is taken this equation, multiplied both sides by k, so that gives me k epsilon k here, k f prime a here, gets rid of this denominator, and then I'm keeping the f of a plus k on one side, although I'm putting it on the left over here, and I'm sending everything else over to the other side. And there's this extra information I want to keep a hold of, such that epsilon of k goes to 0 as k goes to 0. And remember, this is saying that there exists a number f prime of a such that so this I want to settle on as my new definition of the derivative. The derivative of f at a is this special number called f prime of a, which gives you an equation like this. That when you evaluate f at a nearby point, it's equal to the original value of f at the original point a, plus the number k multiplied by this special number f prime of a, plus this error term. And the error term is the special form that it's k times a function epsilon of k, with the extra property that epsilon of k goes to 0 as k goes to 0. This is called the linear approximation. The linear approximation form for f. You can draw a picture, illustrate a picture of this. Space. Okay. So what's the picture? Well, the picture is just the usual kind of picture of my function. So here's my function. Here's, say, the point A. Here's my nearby point A plus k. And really, this is just talking about the tangent line. So we're familiar with this idea of the tangent line. This is the line of gradient f. The value, the gradient of this line is the value of the derivative. This point here, when you bring this point across, comparing it with this point up here, this point brought across is here. So, and then we've also got this value here. Let's call that today. So that's the original point f of a value. This is the original value up here, f of a plus k. This value here, this intermediate value, which is the value on the tangent line at a plus k, that is the value of my f of a plus k times f prime. So I've just written in there, it's small, you see, linear approx. Written in linear approximation in here. Sorry, it's a bit zoomed in. Okay, see it a bit better. That's the linear approximation. Okay. So that linear approximation for the function f that's these first two terms here from the definition of the derivative. F of a plus k times the derivative f prime of a. So this linear approximation for f is the best way to estimate f using a linear function, in other words, a line. The best way to estimate the function with a line close to the point A. And it's the derivative, and the line we're talking about is the tangent line. And it's the gradient of that line is the value of the derivative. This distance here, this error term, go over here, that distance term there, the size of that is my k epsilon k. That's the error. Associated to any approximation, you've got an error, of course. So that difference in value between the true value of f of a plus k and the linear approximation value is this quantity k times epsilon of k. So it'll turn out now shortly when we move to proving the chain rule now, it'll turn out that knowing the structure of the error term like this is the key point. Being able to express the error term as k multiplied by another function. And the other function, so clearly this first factor k, that approaches 0 as k goes to 0. It's just k. It's k multiplied by another function k, which also goes to 0 as k goes to 0. So the work, what we've gained from doing this reformulation of the derivative, because you could say, why did we leave behind this nice simpler version of the derivative? Well, the reason we left it behind is to gain something. And the thing we've gained is this more detailed description of the error term. Before we just had it, well, the distance between these two quantities goes to 0. Okay, fine. But now we know, well, yeah, this is the distance between them. And it certainly goes to 0 as k goes to 0 because it's got a factor k there. But the other factor goes to 0 as well. So it's kind of a more detailed view. We have obtained slightly more detail about the error term. Knowing it's structured like this, k times some function which itself goes to 0 as k goes to 0. Any questions about it? Things you'd like to ask about it, or that I can clarify about that? It is a kind of a new thing. You probably haven't seen it before, but it's a key idea in being able to give a linear approximation to any function. Linear approximations are nice if they approximate the function well, because they're just straight lines. Straight line functions are very easy to deal with. They're very, very quick for the computer to evaluate. It's just a straight line function, some constant plus k times some constant plus k times another constant. Very easy to combine together, to manipulate, to record, and so on. Okay, so now what we want to do is use this to prove the chain rule. Use this now to prove the chain rule. So the chain rule says, just recap it, that if a function y is f after g, then the derivative of y at a is going to be f prime g of a times g prime of a. Okay. Now we need to assume that the two functions f and g are both differentiable. So since f is differentiable well, f we're assuming is differentiable at the point g of a. So this implies that we have the following expression for f evaluated nearby to that point g of a. So if we evaluate f at a nearby point g of a plus k, I'm going to write down now that linear approximation form of the definition of the derivative. Okay? We're assuming that we can write this as f at g of a, the base point, plus k times, we're assuming that this special number exists, which is the derivative of f evaluated at g of a, and that this is multiplying this error and the error function that is here. So this is my linear approximation to f based at the point g of a, and this is the error term here. And it has this form k times, I'm using another Greek letter here, mu. That's the Greek letter mu. The equivalent of RL. M sound in Greek. The Greek letter mu, where this function mu of k goes to 0 as k goes to 0. The linear approximation part. Here. And this is the error term here. So we're assuming that f is differentiable at a. Sorry, f is differentiable at g of a. So we have this expression available to us for evaluating f at a point close to g of a. So you write the Greek letter mu as like our u, but with a long leading tail. Leading tail. Long leading upstroke there. Okay. We also assume that g is differentiable. The g is we're going to be assuming is differentiable at the base point a. G is the first function in the composition, and it's going to be evaluated at the base point a. So that implies by this new definition that we have the linear approximation form for g based at the point a available to us. This is a plus. Now, my little difference of the base point a, I don't want to call it k, because I've already used k for my little difference up here. But if I also use k up here, then the two will be forced to kind of move exactly in step with each other, and I don't want to do that. So I'll just use a different letter. So I'll use an L here. So f at a nearby point a plus L, we're assuming, sorry, g at the nearby point a plus L, we're assuming that this is the value of g at the base point, g of a. Anyway, g of a plus L times this derivative number, g prime of a, plus L times, and I'll use epsilon of L for this error function. We've just had the equivalent thing where epsilon of L goes to 0 and L goes to 0. Okay, so it's a bit of a mouthful, all of this. It's quite lots of more technical detail. But it's what we need to put together. The way I think about it, it's what we need to put together to get to the chain rule first. Okay? So those are the assumptions behind the chain rule, that we've got our functions f and g, they're both differentiable. We're assuming g is differentiable at the base point a, and f is differentiable at the point g of a, because f is composed of g. So these are our two assumptions, and somehow we want to bring them together, in very vague terms, squash them together, amalgamate them, push them together to get the linear approximation form for f after g, for y prime. In that way, we'll have proved that the composition y is differentiable, and we'll discover that this is indeed the correct number to use for the derivative of y at the point a. So the reason different letters have come in here is because I want to have assuming my f and g are differentiable, and I want to use fresh notation for each. So k is my little error term here, mu is the error function, and for g, I'm using L as the little error term, the difference term away from the base point, and epsilon as the error function. Okay? But these two things I've just written down here are just two versions, two instances of my linear differential form of the derivative. Any questions just about setting up those assumptions? We haven't started proving it. We've just taken a lot of effort to write down the assumptions carefully. So now we combine these assumptions. Correctly. Might be lots of incorrect ways to combine them. We want to bring them together to produce the linear approximation equation for y, trying to prove y is differentiable. So we want to construct that linear approximation formula for y with the required number y prime of a. We want to prove, how's it going? We want to prove that this special number y prime of a is indeed this. Okay, we can't assume that it is. That's assuming the chain rule. We're trying to prove the chain. So what we seek to do is discover or construct the linear approximation function or linear approximation equation for the function y and discover that this number is indeed y prime of a. Okay, now I just want to proceed carefully because I want to combine it in the correct way. So we just constructed it directly. So what's on the left-hand side of the linear approximation form? Well, on the left-hand side is y of a plus h. Or, no, I'll write that as l. Yeah. Sorry about that. First cross out. Y of a plus l. So I'm evaluating y at the base point a, and I've got my little distance l away from a. Now what do I know about y? I know y is the composition. So this is f of g of a plus l. Let's just buy the definition of y. That's just how the function y is defined. It's the composition of f and g. So, I want to persuade you how naturally this comes out. This is the left-hand side of the linear approximation form. Y at the base point plus a little error term. I just replace this with the definition of y. Now what should I do next? I've got f of g of a plus l. But on the previous sheet, I've just gone to an awful lot of trouble to construct this expression here for g of a plus l. So I should immediately use it. Here's this equation is saying that g is differentiable, and it gives you this linear approximation equation for g of a plus l. So I'm just going to put that in here. So this is f of, and instead of g of a plus l, I just put in all of the right-hand side here. It's a bit of a mouthful, but that's going to be g of a plus l times g prime of a plus l times epsilon of l. Now I'm looking at f. What am I looking at now? Now I'm looking at f evaluated at the base point a plus this extra stuff here. This extra stuff here is going to be my k. Compare it with the linear Compare it up here with the linear approximation form for the function f. We wrote down a few lines ago. The linear approximation form for f is something you can use when you're evaluating f at g of a plus a little bit. Well, here I am, indeed, evaluating f at g of a plus, okay, it takes a bit to write down, but it is a small number, because L was a small number. L is convergent to 0 in the process. And here you've got L times a constant, that's going to go to 0. And you've got L times this other function, and the other function epsilon L also goes to 0. So this whole number is this small number. So that's my small element k. So I now use the definition, use the linear approximation form for the function f to write this as f of g of a plus my k. This is my number k, so L g prime of a plus L epsilon of L. And this multiplies by the derivative of f evaluated at g of a. And then I've got my k again, but I'm actually going to write it as k here just to save space. K times mu of k. So this k I've introduced here is exactly this quantity here. Now I've written it out here in the brackets if I want to expose it a bit. So now what I do is I expand out this multiplying bracket here. So still got f of g of a at the front. Then I'm going to have my L here, and that's multiplying f prime g of a times g prime of a. So that's this multiplied by that. Oh no, frankly, I do have to expose it. Just L. Yeah. Then I've got the L times epsilon L times f prime g of a. I'll continue that bracket and write k over L mu of k. Sure. Sorry about that. But this here is this outside large square bracket. It's L multiplying into all the And that's kind of it. What we'll just have to do now is just pause and look at what we've got there. We've got our function y evaluated at a nearby point to L, a plus little l. And here it is. This is exactly y of a, f of g of a, plus l times this number. And note that that's the required form for the derivative of l. It's the derivative of f evaluated at g of a multiplied by the derivative of g evaluated at. And this here is all error term. This here is linear approximation. Linear approximation to y. And we just note that the square bracket term, that's everything inside this square bracket, does indeed converge to 0 as L goes to 0. part of noting that would then be k goes to 0 as L goes to 0. So k, which is this expression here, that does indeed converge to 0 as L goes to 0. So I have successfully constructed the linear approximation form for the function y. Because it's the value of y at the base point A, the small difference L multiplied by this fixed number, which has the required form to be the derivative of y. And then the error term is all L times a function of L. And that function of L, that everything in that square bracket, has the property that it converges to 0 as L goes to 0. So this is the required form. This is indeed the required linear approximation form for L. The linear approximation with error term, required linear approximation equation for L, where the error term has the required convergence property. It's expressed as L times a function of L, and the other function of L converges to 0. So the last point is, and we discover the correct linear gradient term f prime evaluated at g of a times g prime. That term there multiplying the L in the linear approximation. So that's the proof of the chain rule. It's very, very different feel to the proofs of the linearity and the product rule and the quotient rule. Although remember, the quotient rule, we made use of the chain rule in order to prove it. So there's a lot of detail there. That's perhaps the most sophisticated argument or complex technical argument you're going to see in unit. But I think it's nice to see. It's nice to see us form the definition of the derivative, take a very detailed look at it. That work we did to reformulate the definition this morning is just like really looking very carefully at everything in the definition of the derivative. And then we saw how we can put it together with the two component functions to prove the chain rule for the composition one. Okay, we're going to leave it there today. Next week, we'll make a bit of progress with this chapter by looking at the applications of differentiation. So you can probably be looking ahead at those. These are the section which starts at the bottom of page 47. Those topics will occupy us next week and in the tutorials next week. Okay? The scans of these pages will go up after the lecture recording as usual.